Let's see another example where given a language, we want to prove that it is not context-free. The language is defined as follows. L is WW such that W is in 0, 1, star. Okay, we want strings such that if we divide the string into two equal parts, the first part should be exactly the same as the second half of the input string. Okay. Let's first try to imagine if we could come up with a PDA that recognizes such a language. We had already seen actually a language that is related, and we could design a PDA for that. The language was WW reverse. So if we divide the string into two, the first part is the reverse of the second half of the string. For such a language, we were able to design a PDA. For that, what we were doing was reading the input symbols, processing the input symbols for the first half, and for every symbol that we process, we push the corresponding symbol into the stack, and at the same time making a non-deterministic guess that we have reached to the middle of the string. And for the second half of the string, once we consume every symbol in the second half, we try to pop the corresponding symbol from the stack. And if we are able to do this until the end of the input processing and the stack becomes empty, then we know that the string is in the format WW reverse. However, now the language definition is different. We want the first half of the string to be exactly the same as the second half. If we were to apply a similar idea as the previous language in an imaginary PDA, we would be pushing all the symbols in W in the first part of the string into our stack, but then the position of the strings stored in the stack for the second half would be in opposite direction, so that the first symbol in the second half that we want to check actually would lie at the bottom of the stack. To be able to compare them, we would need to empty the stack, in which case we would be losing all the information that we stored regarding the first half of the string. So such an idea will not work for this language, and we can guess that the language is not context-free. However, to prove formally that the language is not context-free, we will need to use pumping lemma. To use pumping lemma, to show the importance of choosing a special string, let's first choose a string S that will not work using the pumping lemma. Basically, let's choose a negative example in this case. Let's assume that we choose the following string S. So basically a bad choice. This is an example of a bad choice of string S in pumping lemma. Let's say that we have chosen S to be 0 to the P, 1, 0 to the P, 1. Let's first see if this string is okay to use in our pumping lemma. To be able to use such a string in the pumping lemma, remember we had two conditions. One is that the string must belong to the language. Let's check this condition. So if we divide the string into exactly two equal halves, this will be the middle. The first half is 0 to the P1, the second half is 0 to the P1. So it's in this format, therefore the given string is inside the language. And our second condition was that the length of the string should be greater than or equal to P. The length of the string is actually 2P plus 2, so it satisfies this condition as well. So theoretically, we can use this string S for the remainder of our proof using pumping lemma. So our pumping lemma says that the string S is divided into 5, partitioned into 5 u, v, x, y, z. Let's try to visualize how it looks like. We have P many zeros, followed by a single 1, followed by P many zeros, followed by a single 1. This is how our string S looks like. Let's see, as was the case for the previous example, if we can consider every possible case for the middle substring vxy, and for each case let's try to see if we can show that there exists some I such that uv to the I xy to the I z is not in the language. Okay, so for this we would, for instance, we could first start with the assumption that vxy consists only of one type of a symbol. So vxy is somewhere among the zeros in here, or vxy is the symbol 1 itself, or vxy is among the zeros in here, or vxy contains only the symbol 1. Let's consider the first scenario. Vxy is among the initial zeros. If this is the case, then it's easy to see that if we consider uv square xy square z, since v or y is not epsilon, in this first part we would be increasing the number of zeros. So the number of zeros in uv square xy square z is now going to be greater than p, and followed by 1 symbol 1, followed by p zeros, followed by 1 symbol 1, because we didn't do any modification in this part of the string since we assumed vxy was here. Now under this case, it's clear that the new string will not belong to our language L, because the new middle of the string will be somewhere among the zeros, so that the first half of the string will consist only of zeros, whereas in the second half we will have 2 symbol 1s. Therefore, the new string will not be in this format, and the new string will not belong to the language. So in this case, for this case, we were successful to show that there exists I, basically I is equal to 2, such that uv to the I xy to the I z is not in the language. We can do the same thing for the case where vxy belongs to the zeros in the second half as well. Okay, and the same thing can be done assuming for the case where vxy is simply a 1 in here, because we know that v or y is not epsilon. Then pumping v and y twice, so basically uv square xy square z, again now the length of the string will be now more than 2p plus 2, so that the new middle will basically slide to the left a little bit, and the right half of the string will not be the same as the left half of the string. Therefore the new string is not in the language. However, a complication arises in the following case, where vxy, the string where we base all of our subcases on, for the scenario where vxy contains 2 types of symbols. For instance, for the case where vxy is, let's say, somewhere here. So for this case, you should be able to see that now we have a difficulty, because not under all possible scenarios it is possible that we can find an I where uv to the I xy to the I z is not in the language. Because consider the following scenario where, consider v is, let's just say, simply 0. So v is basically this symbol, v is 0, and let's just say x is 1, this symbol 1, and let's say that y is just this symbol 0. Okay, basically v is 0 here, x is this 1, y is this 0. For this scenario, for this case, we can see that we cannot find any integer I such that uv to the I xy to the I z is not in the language. Why is this true? Because v is the same as y. V is 0, y is 0. Let's just consider uv square xy square z, for instance. In that new string, we will be increasing the number of zeros to the left of the symbol 1, but however many symbol increase that we have had, we will be doing the same thing for the right substring, for the zeros to the right of the symbol 1, because y is as well 0. Okay, So the same goes for uv cube xy cube z as well. Okay, the number of zeros to the left of 1 will be the same as the number of zeros to the right of 1, of the symbol 1. If you consider any integer I, you will be able to see that however many zeros we have introduced to the left of the symbol 1, we will be introducing that many symbol zeros to the right of the symbol 1 as well. Therefore, for any I, uv to the I, xy to the I, z, the new string will always belong to the language L, since the right half of the string will be the same as the left half of the string. So this is where the difficulty lies. This implies that the choice of this string S was not good. This implies that choosing S equals 0 to the P1, 0 to the P1 does not work for our pumping lemma. Okay, does this imply that the language is context free, since we couldn't prove yet using our pumping lemma? This actually doesn't imply that, because it may just be the case that only this string did not work using our pumping lemma. Only this string was not a good choice. So it can still be the case that if we choose yet another particular string where we will have all of our pumping lemma work properly, if that's the case, that's good enough. That will still show us that the language is not context free. So as long as we find a good string S such that the remainder of the pumping lemma works properly for every possible partition, then it implies that the language is not context free. So for the remainder, we will actually give now such a string S where the string S will work for our pumping lemma.